I will say some of these questions in the beginning here are a little more involved entirely than what you would probably see on the exam, but they're a good practice for all of that. So again, we've had these sort of bowel prep questions before because a lot of these electrolyte bowel preps are osmotic because of, we'll calculate milliosmolars because of the electrolytes. So the first part of this question says, let's calculate milliequivalents as a good review, starting with potassium, and then we'll do sodium, and then we'll move on to the osmolarity of the entire solution. So as far as calculating the potassium, there's only one source of potassium in that formulation, which was the potassium chloride, and it said there were 3.2 grams of potassium chloride. So I'll try to go through this quickly because it's kind of a review, but this is where I still think a lot of you can go back and review. This was the hardest exam, unit exam 3, chapter 12, I would say. Look at those practice problems until you can kind of get this ironed out. But we got to start with the weight, and our weight is in grams, so let's convert grams to milligrams because we're going to eventually want milliequivalents. So let's get everything into milli. So 3.2 grams times 1,000 converts that weight into milligrams. Then to convert a weight, the first step is to go to the number of molecules. And remember, to convert a weight to molecules, we use the formula weight, knowing that the formula weight in milligrams is equal to 1 millimole. So this is why I can multiply for every 1 millimole of potassium chloride, there is 74.5 milligrams, and that's coming straight from the molecular weight that I will give you. So if I stop my calculations at that point and come up with my number, you'll see that 3.2 grams is 3,200 milligrams is equivalent to 43 millimoles of potassium chloride. So let's restart with that. Now that I have the number of molecules, parent molecules, I can count the number of potassiums in those molecules. How many potassiums are in a potassium chloride? Look at the formula. How many is there? 1. You'll see here in a little bit that's not always the case, but in this case, 1 potassium for every 1 potassium chloride. So now I've converted from potassium chloride to potassium. And let's look at the valence. Remember, milliequivalence is all about the charge. Since potassium has a +1, meaning there's 1 milliequivalent for every 1 millimole. So by multiplying by that, I know it doesn't change the number, but my units get changed to milliequivalents. So 43 millimoles is equal to 43 milliequivalents for potassium, since its valence is 1. You get 1 charge from every 1 molecule of potassium. All right, so that is the answer for the number of milliequivalents of potassium. All right, I'm going to kind of quickly show through one example and work through all of the sodiums, because in this prep, there are 3 sources of sodium. So starting with the first one, the sodium bicarbonate, look at, I started with grams, and I converted them to milligrams. And then from milligrams to millimoles by dividing by the molecular weight. That gave me millimoles. And again, much like potassium, sodium has a +1. So as long as there's only 1 molecule in every 1 parent molecule, then again, 1 charge for every 1 millimole, you can see that you get the same number, all right? So as long as there's only one of those ions and the charge is 1, then the number of millimoles is equal to the number of milliequivalents, all right? And you can see that's the same way with sodium chloride, because it's 1 sodium for every 1 sodium chloride. Well, the only thing that gets different, if you want to practice on this, the sodium sulfate. Let's look at the formula there. It's different because there are 2 sodiums in the parent molecule. So quickly, we start with 22.8 grams. We multiply by 1,000 to get to milligrams. We divide by the molecular weight to get to millimoles. Nothing is different yet. Starting with those number of millimoles, what's different when you look at the millimoles of the parent molecule? When we want to know about sodium, we need to know that there are 2 sodiums for every 1 sodium sulfate, and that comes right off of the formula. You have to look at the formula there. You see where it's Na2. So that's where I got 2 sodiums. This doesn't change though. There's still only ever 1 milliequivalent of sodium for every 1 millimole of sodium because the valence doesn't change. 1 charge for every 1 molecule, but this tells me for every parent molecule I get 2 sodiums. So that's where it's 160.5 times 2 to get to 321 milliequivalents of the sodium from sodium sulfate. So again, practice on that one. And again, they're not always this way, but you have to double check. There's certainly definitely times where you have more than 1 ion or element in a parent molecule. Okay, so just so you can see the final answer, when I add all those up, my 3 sources of sodium all together, I got 505 milliequivalents of sodium from all 3. All right, now let's talk about the osmolarity. Osmolarity, and I'm going to go ahead and show this first one, and the one that we haven't dealt with yet was the polyethylene glycol ingredient. There was 240 grams of that. So if I convert my 240 grams of PEG to milligrams, and then milligrams to millimoles by dividing by the molecular weight, this is the same process we've talked about this far, to go from the weight to milligrams and from milligrams to millimoles. Now, PEG is like dextrose or like glucose or like any other non-ionic compound that does not dissociate. It stays together. And if it doesn't dissociate, if I have one parent molecule, how many molecules do I have in liquid? One. It's 1 to 1. It's a non-electrolyte, meaning there is one particle for every 1 millimole. All right? So that gives me 72 milliosmoles. All right? So there we have it. The trick now is, if we look at the other ingredients, potassium chloride is, and again, if I start with the millimoles, since we already solved for those, or those numbers we already have, just starting with the number of potassium chloride in millimoles, 43, it does dissociate. It dissociates into how many things? 2, 1 potassium and 1 chloride. I get 2 things, 2 particles for every molecule. So if I have 43 molecules to start off with, I'll end up with 86 particles when I'm all done, and the particle count is called milliosmoles. So again, 43 millimoles becomes 86 milliosmoles for potassium chloride. You'll see that's essentially multiplying by 2 for each of the sodium bicarbonate and the sodium chlorides. But remember our special drug here, sodium sulfate, that has Na2SO4. When it dissociates, you get 2 sodiums, remember, and 1 sulfate. So the total number of particles is 3. So we take its millimoles times 3 to convert from the number of parent molecules to the number of particles generated in solution by those parent molecules, which would be 3 times the number of particles. Okay, add all of those particles up, and I tell you now, my question, there will probably be one on osmolarity. It will always be about osmolarity, which is the number of milliosmoles per what? Per liter. You got to have the final number in per liter. So this step is just adding up all of those individual milliosmoles, taking the millimoles times the number of particles, adding them all up together. So everything combined has that number of milliosmoles. But in what volume? That volume, I need to express it per liter. How many liters am I making? 4 liters, and express it as liters. So I can divide my total milliosmoles by my total volume in liters, which is 4 liters. When I divide that out, then my osmolarity is 252 milliosmoles per liter. Okay? All right, so that was that one. Now this one, I'll be honest with you, I'm going to go through kind of quick here for the sake of time. It's tricky. This one is not a great example of what you'd expect on the final exam, but if you can do this one and if you can understand it from the key, you're in pretty good shape. So let me just try to start off with this. You know, I like this one because this is a complicated drug that's got 2 things in it. It's got magnesium salicylate and choline salicylate, and there's 2 different concentrations. The concentrations of each in the solution are not the same. All right, so that's a little challenging. What's also very challenging is the active ingredient. What is the active ingredient? It's not magnesium, and it's not choline. It's what? Salicylate. What we really want to know is how much salicylate is in there. Remember, what is aspirin? Acetylsalicylic acid. Again, the active part of aspirin is a salicylate moiety. So again, what's different here is how many salicylates are in magnesium salicylate. You got to look at the formula for that. It's Mg salicylate 2, all right? There are 2 salicylates for every 1 magnesium salicylate, whereas for choline salicylate, there's only 1 molecule, all right? That makes this a little more challenging to understand. So again, in terms of trying to determine the weight of salicylate, it wants to know the weight of salicylate, you have to do them separately. You have to figure out how much weight is coming from the magnesium salicylate, and then do this for the choline salicylate. So all of this work that you see here is just for the magnesium salicylate. But I want you to realize here, there are 2 different methods of doing it. This is kind of the way I think of it in general. I like to go step by step through my basically dimensional analysis. But if you like the cheaty way, I'm all for that. You can do this. But this goes back to chapter 20 when we did moiety over compound. Are you with me on that? So let me just explain moiety over compound. Because would you agree, our moiety is salicylate, our compound is magnesium salicylate, all right? So the first thing you still have to do in both methods is figure out how much compound. How much magnesium salicylate is in a tablespoonful if it has this concentration? Okay, so I just use the concentration times 15 mils, and what we're saying here is for every tablespoonful, that's the amount of magnesium salicylate I will have in it. But I want to know salicylate. I got my compound, but I want my moiety. The only issue here, so do you see where here's my moiety, here's my compound, here's the molecular weight of my compound, but I'm going to take my moiety molecular weight, and what am I doing to it? Multiplying it by 2. So if you're going to set up the ratios of the molecular weights of the moiety to the compound, since you have 2 moieties in the compound, you have to multiply the moiety molecular weight by 2. But if you do that, if you have 137.1 times 2 above 298.5, set that equal to X over the amount of compound that you have, you will determine that you get 998 milligrams of salicylate, the moiety. So this is definitely an easier way for a lot of you than thinking through this method. And I won't go through this all, but you can see I go from volume to milligrams, from milligrams to millimoles, from millimoles of the compound to the millimoles of the moiety, and then multiply by the molecular weight of the moiety to get its actual weight. So there are multiple ways of doing it, okay? Doing the same exact thing for the choline, and I'll just leave you the stuff on top. How many salicylates are there in a choline salicylate? 1. So we can set just the 1 molecular weight of salicylate over the 1 molecular weight of choline salicylate. So moiety over compound. I've solved for how much compound I have. So if I set up that proportion, I can determine how much moiety I get. Okay? So this is absolutely going back to chapter 20 to do it the quick way. Or you can do chapter 12 and do it the longer way. And again, both methods will be in the key if you want to be able to look through that. So once you have found the weights of each of the salicylate from each ingredient, so from the magnesium salicylate, I get this amount. From the choline salicylate, I get that amount. Add it all together, and I can see my total weight. Right? So that's where that comes from. Now, it's asking for the osmolarity. And I think for the sake of time, I'm not going to go through this in detail. It's the same process. But in the end, when you know the number of molecules, again, look at the formula of magnesium salicylate. How many particles are there? 1 magnesium, but 2 salicylates. So that's why there's 3 times its number of molecules to get to the milliosmoles. Whereas when you look at the choline salicylate, there's 1 particle here, 1 particle here. That's why there's a 2 there. All right, so it always goes back to the molecular formula in terms of doing those. All right, and again, there we go. So let's focus on some of the other ones we can try to accomplish on the amount of time. This was a pretty straightforward dosing one where it says the dose is weight-based, so it's not body surface area. It's 6 milligrams per kilogram, and based on ideal body weight. Unless they're obese, which means you have to use adjusted body weight. So before we calculate the dose and determine the infusion rate, because again, we're going to add our dose to a 50 ml bag and then infuse it over 1 hour. So this is a chapter 13 thing where not only do you come up with the dose, but you have to infuse it and come up with an infusion rate. Okay, and I will give you all of the dosing formulas. So you don't have to memorize any of those, you have to use them correctly. So let me just go through our first example here. With our 53-year-old male patient, let's take their weight and determine their weight in kilograms. All right? Let's take their height and determine their height in meters. And I gave you those conversion factors. Why? Because the BMI formula uses their weight, their actual weight, and their actual height in meters, and calculates the BMI, the body mass index, the weight in kilograms divided by the height in meters squared. All right? And that came out to be 31. If you remember, we said above 30 is considered obese. Since they're 31, it means we have to use the adjusted body weight for their dose. Remember, adjusted body weight starts with the ideal body weight. So you always have to start calculating with the ideal body weight. And I will warn you, the only trick with ideal body weight is it's different by gender. So make sure you choose the correct starting formula based off of the gender. Since this is a male patient, we're going to take 50 kilograms times 2.3 times every inch over 5 feet. He's 5 feet 9, so 9 times 2.3 plus 50 gives me an ideal body weight of 70.7. Okay? The adjusted body weight formula takes this number, okay, and finds the difference between his actual and this ideal value. The difference times 0.4 is then added to the ideal body weight. So doing all of that math, we find out that the patient's adjusted body weight is 81 kilograms. That is the more reasonable weight to base his dose on. So let's take that weight. Now we've done all that work just to figure the weight to use. But now that we know he's 81 kilograms, it's 6 milligrams per kilogram. So that's easy enough. That gives me 486 milligram dose. But I need to figure out how much liquid additive will provide that dose. It's an injectable solution. So it comes in 500 milligrams for every 10 mils. So if I divide or multiply by 10, divide by 500 so that milligrams cancel, I determine that I need 9.72 milliliters of the drug solution. So far, so good? The trick with that is we are not going to just inject it. It has to be diluted. What did the question say we're going to dilute it in? An additional 50 milliliters. So to this volume, we need to add this volume. So remember, the volumes are additive. So ultimately, the volume I'm going to infuse in this patient is both the diluent and the drug of 59.72 milliliters. That's the volume I have to administer over 1 hour. It told me that in the question, to administer it over 1 hour. So that's where the 59.72 milliliters per hour comes in. But it wants an administration rate in drops per minute. So we have to convert all of that. So since we're using a set that delivers 12 drops per mil, I can multiply by 12 and that'll convert mils to drops. And since I want it per minute and this is in per hour, I need to divide by 60 so that hours cancel. And you can see doing this, I get drops per minute. So multiply 59.72 times 12 divided by 60 gives me, in rounding, I get 12 drops per minute. Okay? So, traditional process. I think you guys did well with chapter 13. This was, again, practicing your weight-based calculations, having determined body mass index, and based off of that, determining ideal body weight. Based on that, determining adjusted body weight. That's where the majority of this work was getting the right weight. But once you have the right weight, I would say the trickiest thing is I think usually this part of it you guys can do pretty well. Don't forget, though, that whatever that equals to, read the question. If you add that to a volume, then you have an additive volume. If you added up to 50 milliliters, then your final volume will be 50 milliliters. So read that part of the question carefully to know what's happening with the drug volumes. All right? And I will skip this one because it works the same way. All right, let's do chapter 15. And I like this question. Again, this review is harder question-wise than what you would see on the test, but this allows me to kind of practice both things. Because here I have 1.5 ounces of clindamycin and benzoyl peroxide being added to 2 ounces of erythromycin and benzoyl peroxide. So I've got 3 ingredients. I got clindamycin, benzoyl peroxide twice, and erythromycin. And we're mixing all of those together. So again, clearly we're going to be fortifying the benzoyl peroxide, but we're going to be diluting the clindamycin and the erythromycin. So again, this one I had set to work by algebra, and again, you can do it in any method you want on the test. But the first thing to do is to get rid of these things. Man, those are terrible numbers there. I hate ounces. Let's convert it to grams. Remember, convert things to percent concentration and to the same units of weight. In this case, we can do grams. So the 1.5 ounces, basically, given the conversion factor, just means that first cream that we're going to be using is 42.5 grams, whereas the second one we're adding to it is going to have 56.7 grams. And you know, while we're here, and now that I know the weight of each cream in its weight, when we mix those together, what will the final weight be? The combination of those two weights. So let's go ahead and figure out the total weight when everything's added together is this. So here's ingredient 1, here's ingredient 2, and here's the ingredient 3, or the final mixture. So do we know all of our Qs? I would argue we know Q1, we know Q2, we now know Q3. The Qs are not the problem here. So pick one. Which one do we want to start with first? Clindamycin. So let's start. What is my initial concentration of clindamycin? 1.2%. We already know the weight from our previous calculations, so we have the mass that we're starting with in our first cream. When we add the second cream, how much clindamycin is in there? 0, man. We're not getting anything, but we know its weight. So its mass will be 0, so I can ignore all of that. My final mixture will have what concentration of clindamycin? I don't know. It's X. But remember, I know the final weight. It's going to be the additive of all those weights, so I know its weight. So really, I have this is going to equal this. So let's bring those down here and just set them equal to each other. So 1.2 times 42.5 is 51 times equals 99.2x. Divide each side by 99.2. And I get 0.5. And it should make sense that I'm going from 1.2% down to 0.5. I'm diluting it. There's going to be less concentration of clindamycin. All right? On the other hand, benzoyl peroxide is in both ingredients. So again, the first one has 5% in this weight. The second one has 5% in this weight. And when we mix those together, I don't know what the combination will be, but I know what its final weight is. So again, this mass plus this mass, there's 1, there's 2, equals number 3. If you do the math, then you multiply those out, equals still the 99.2x. You divide by it, you get 5%. That kind of makes sense. If you start with 5%, and you add 5% to it, what do you think the final concentration is going to be? 5%. It doesn't go up, but it doesn't go down either. It maintains that concentration. So while the concentration didn't change because both ingredients had the same concentration when we added it, okay? And I'll kind of go just show you the numbers here. For erythromycin, it's much like the clindamycin. There is 0 in the first cream, so there's nothing from it, but the second cream has mass, and the final cream will have some mass, so you just set the one equal to the other, and you see that ultimately you get 1.7%, which again is going to be down from the 3% that we started with. So again, it did decrease. All right? All right. So on the exam, I will still tell you, whenever these questions, you can do them by either algebra or alligation. Here, let me show you the alligation method quickly for this. Here we got 10 milligrams per mil. We need to convert that to a percent. So basically, I want to combine a 1% with a 0.3% and end up with a 0.75%. So that's 1%. 0.3% to get 0.75. So I set up my alligation, high on top, low on the bottom, desired here. Cross what? This is always what you guys forget. Subtract, so a 0.75 minus the 0.3 gives me 0.45. 1 minus 0.75 gives me the 0.25. All right? So remember, P's over Q's, since the only quantity I know is the 5 milliliters of the 0.3%, so I know this parts, so the parts from the 0.3 go here, 5 milliliters go there. I know my parts from my injectable go here, and I'm solving for this. This is what I want to know. So use this relationship here to solve for it, and you can see that that's 9 milliliters. Okay, I know you're anxious because I'm running out of time here. I will leave these here on the questions here. This one is pretty straightforward. It wants to know the plasma concentration was just the dose over the volume of distribution. The trick is that I need it in micrograms per deciliter. So make sure you convert your weight here to micrograms and this volume to deciliters. This last one, part 2, is an endless practice problem for chapter 22. So feel free to look at this, but if you want to practice that some more, there is an endless practice problem for the pharmacokinetic chapter, guys.